The first question that we have today is about Boyle's law. That is early, right? Here we go. So the idea behind Boyle's law is just that pressure is inversely related to volume. And so it's just saying that this is what we think about when we're talking about increasing lung capacity. So if, at rest, your diaphragm is shaped like this. And so your lungs are sort of relatively small. And then when you compress your diaphragm, what happens to it?
It
goes down.
It flattens.
Yeah.
And so then what happens to the volume of your lungs?
Increases.
And so then if the volume increases, what happens to the pressure?
Decreases.
It decreases. And what does that mean in terms of movement of air?
It goes in, right?
Yeah, it goes into the lungs because everything will go from high pressure to low pressure. So if we're trying to move air out of something, we want to decrease the volume. And if we want to move air into something, we want to increase the volume because that will change the pressure gradient and cause the air to move in that direction.
Okay, that makes sense.
Did you have a specific question about that beyond that, or that was...
No, I just couldn't remember, how they were related to one another.
Okay,
so.
Yeah. Other questions? I should have made a Kahoot or something. I thought you guys would have lots of questions.
Can we go over those questions with the graphs for respiration that we did in class?
Yes, we can review the respiration stuff. So, you want to look at the game, right? Is that what you're talking about?
I think we did when we walked around the classroom and you had all those. Okay, yeah, that.
And what do you see on your screen right now? Do you see anything?
No? Yeah, we see the PowerPoint slide.
Okay. So I have to share something different. Okay, so can you see this now?
Yeah.
Okay. So view, page width, all right. And I have different piles here. I made different piles of stuff. So respiratory stuff is somewhere. Here we go. Okay. So your question is specifically though about the oxygen dissociation curves. Is that what you were wondering about and wanted to review?
I think so. Wait, will you scroll down? It's
yeah. So this part is more straightforward, right?
Mm-hmm. I think that's fine.
Yeah, and then the compliance, I think people were okay with.
Yeah, that's.
And heart failure. And the problems, were you guys okay with these problems? Sort of?
Yeah, the dead space problems.
Dead space and all that.
Mm-hmm.
And then, okay. So then this is where I'm guessing the issues are.
Mm-hmm.
Oh, yeah, how they change, yeah.
How they change. That's what everybody doesn't like, yes?
Yeah.
Okay, so what we're looking at is, well, actually, maybe I should show you, do you want to look at the PowerPoint slides first, or about this?
Either way.
Either way. Okay, so this one is just showing you percent oxygen saturation of hemoglobin, and then it's showing you the partial pressure of oxygen. So as partial pressure of oxygen increases, then the percent saturation of oxygen also increases.
I think I get that one, the one that I was really confused with.
Let me just do my thing.
Okay.
And then, so then this is kind of showing you where you would find, this figure is showing you about the alveoli, or where you would find the highest partial pressure of oxygen. And so this would be this part of the curve up here. And then the resting cell would be around here. And then this is where oxygen is unloading. So that's often what we're concerned about, is whether or not oxygen is going to load or unload in a particular area. So for this one, the first question was just asking, when the partial pressure of oxygen is 20 millimeters of mercury, what is the percent saturation of hemoglobin? So you just had to look at this and, figure that out. So that one I think wasn't too hard. And then at what partial pressure of oxygen is hemoglobin 50% saturated? For this one, you look for the 50% saturation, and then you find the point where that happens. So I think that part was probably okay, right?
Mm-hmm.
Where it got a little bit dicier is when we start looking at the different graphs and how they shift to the left or the right. Yes?
Yes.
Okay, so what this is just showing you is how, what we're going to be, when we're going to be unloading oxygen and how it's going to differ depending on pH, temperature, or CO2 partial pressure. So in this case, like when will these things change? Like when will you see a decrease in pH? When will you see an increase in pressure? When will you see increased CO2? When you're doing what?
Exercising.
And now I've been washing my hands so much, my hands are super dry. Otherwise, it's going to bug me the whole time. Okay, so when you're exercising, all of this stuff is happening, right? And so at that point, what do you want to do with your oxygen? Do you want to keep it on your hemoglobin when you're exercising?
Yes.
No.
Oh.
You want to unload it into your tissues.
Oh,
yes?
Yeah. Mm-hmm.
Because the tissues need it at that point, because you're using up a lot of oxygen at that point. Okay?
Right.
So how does the body take care of this? Well, you can see at the same partial pressure of oxygen in the blood, you can see that there are different curves. And what these different curves are telling you, that at different points, you're going to be unloading oxygen into the tissues. So it becomes much easier to unload the oxygen in the tissues when the need for it is much higher. So when we look at this first pH curve, if we're looking at a partial pressure of oxygen, that's just say 40, which is like on the previous diagram, we said that was pretty much like a resting cell. So at 40, we could see that our hemoglobin here, it shows that it'll be about 60% saturated. But at a higher pH, it'll be closer to like 80-something% saturated. Because at that time, the signal is telling your body there's exercise or something going on. That means there's a high risk that we're not going to have enough oxygen here, so we need to unload it into the tissues. So all these things are showing you is that under all of these circumstances, the curves are shifting to the right. And the part of the curve that we are looking at when we say that it's shifting to the right is, remember, this steep part where we're looking at where the oxygen is unloaded. So that part is shifted to the right. So that means at the same partial pressure, we'll have more oxygen unloading in the tissue because there's going to be a higher need for it.
So if there's a higher percent saturation of hemoglobin, that also means that there's more being unloaded. Is that right?
No, if there's a higher percent saturation of hemoglobin, it means it's sticking to the hemoglobin and not going into the tissue. So on this one, like when the pH is 7.6, more of it is sticking to the hemoglobin. If when the pH is 7.2, more of it is unloading in the tissues. Because if we have a partial pressure of oxygen of, let's just say 50, well, let's pick a low one, like 20. So at 20, that's going to be an area where that's like something that needs oxygen, right? So what we're doing there, like if we have just say a pH of 7.4 is a normal pH, because remember normal pH is 7.35 to 7.45.
Mm-hmm.
So in a normal cell that has metabolism going at a normal pace, at a partial pressure of about 20, I don't have my glasses on, but you can see that only about 30% of the hemoglobin is saturated in that area. That means 70% of the hemoglobin, assuming that there's enough oxygen, in the blood, has been unloaded. Like only 30% is attached, 70% has been unloaded, relatively speaking. But then if we have a lower pH, we can look and we can see that at that same thing, it's like maybe only 25% is saturated, meaning that 25% of the hemoglobin is still holding on to its oxygen, and the rest of it has already delivered the oxygen to those tissues. You still don't look convinced, Carmen.
I think I'm confused on like still the partial pressure of oxygen. Is that referring to like in the blood?
In the blood. Mm-hmm.
So like what you're saying about if you're at 20, that's like a low partial pressure of oxygen.
Right. Mm-hmm.
Which
that means there's not very much free oxygen in your tissue at that point.
So would that
free oxygen is what we care about. The free oxygen is what can actually do what we need it to do and be important for cellular metabolism. If it's bound to hemoglobin, it's like bound up, it's like glued onto something and it can't be used.
Right.
Wait, so the percent saturation of hemoglobin, that's the one that's bound? And then the partial pressure is like what's in the tissues?
Well, yeah, exactly.
Okay.
So
that makes sense.
That's why when we were looking at this earlier, if we're at a really high partial pressure, that's looking at alveoli, because that means that there's a lot of oxygen available, right?
Yeah.
There's a high partial pressure of oxygen in the alveoli because that's where the lungs are getting their gas. And then we know that at that point, the hemoglobin will be mostly saturated because most of it will be binding to hemoglobin. It's just telling you like sort of like the direction of where it's going. If it's bound to the hemoglobin, it means that it's probably in some place with high oxygen that's being picked up and taken to some place that needs the oxygen. So in the alveoli, you'll have a high partial pressure of oxygen, and then you'll have a lot of it bound to hemoglobin because it's ready to go through the bloodstream and end up in the tissues. But at a low partial pressure of oxygen, that's somewhere where there isn't very much oxygen because it's being used up by metabolic processes. So in your muscles, you are burning up oxygen all the time as you contract muscle, remember? Because you're generating ATP, and that ATP is going to be powering those muscle contractions. In order to make that ATP, you need oxygen. And so you're going to be using it up a lot. And so instead of having it bound to hemoglobin at that point, you need it to be spilling out and being available to the mitochondria to pick up and grab and take and use up so that they can generate more ATP for your muscle contraction.
Okay.
So what's still confusing about this?
So partial pressure of oxygen refers to free oxygen in the blood.
Yeah. Mm-hmm. Or the tissue or whatever we're talking about, yeah.
Okay, so then how would like if you see percent O2 saturation of hemoglobin, if that's at like 40 per se, and then like, but you were saying that there's like, what's the other 60%?
So if that's, I mean, all it's just saying is that of all the hemoglobin that's there, 40% of the slots that could be filled up by oxygen are filled up by oxygen.
Got it.
So that means that there's lots of room for other oxygen molecules to be binding, but they're not binding because they're being delivered to the tissues instead. Those oxygen molecules can be in one of two states, basically. They can be either bound to the hemoglobin or they can be free.
Okay.
And so if they're not bound to the hemoglobin, they're going to be free and available for the cellular needs of the tissue.
But when partial pressure of oxygen gets bigger, why is more of it bound to hemoglobin? Like, would it be down if more of it was in tissues?
Well, this is saying, like, where do you have the highest partial pressure of oxygen in your body?
Lungs.
In your lungs. So if you are somewhere like that, what do you want to do with your oxygen? Do you want it to be free?
Yeah.
No. Actually, you want it bound. Why do you want it bound to hemoglobin?
Oh, so it can leave?
So it can leave, and where is it going to go?
To your other tissues?
To tissues, right? So in your lungs, you have a high partial pressure of oxygen. And at that point, what you should be doing is you should be grabbing up all the oxygen, putting it on the hemoglobin so it can be carried by the red blood cells to like your toes or wherever else you need it. So where you have a high amount of free oxygen, it should be being grabbed up by the hemoglobin. And where you don't, you want it to be, if you don't have much free oxygen, then you want to be taking it off the hemoglobin and giving it to the tissues.
Okay.
Okay. I think that makes
So
sense.
just say, you can just sort of imagine a red blood cell full of hemoglobin near your lungs, in the capillaries of your alveoli, right?
Mm-hmm.
At that point, the oxygen molecules, there's a high partial pressure of oxygen. So the oxygen molecules do what? in your lungs, what are they going to do to the hemoglobin?
Bind to
Bind
it.
to it.
Bind to it. And so then they go traveling around through the body, and just say that red blood cell ends up in your gastric meatus or something like that. So what do you think the partial pressure will be in your gastric meatus? Is it going to be high? No, because it's pretty far from your lungs, right? So it's traveled a long distance, it's there, and so what does the oxygen need to do at that point? Should it just continue on its journey through the body?
No.
No, it should be really.
It should unload, right, and go visit the tissues.
Yeah.
And so at that point, when we look at that same, because the partial pressure of oxygen will be lower, just looking at a normal curve like the first ones we were looking at, this is saying that when we're at the alveoli, it's likely to be stuck to hemoglobin. But as we go to a resting cell, it's less likely to be stuck on the hemoglobin. And if we go someplace that's using a lot of oxygen at that particular time, it's really going to be unloaded there. So it will be unloaded where it's needed. You don't want it unloading in the lungs because that doesn't help you. You want it unloading in the tissues that need the oxygen the most. So if your brain cells while you're taking your exam are using up a lot of oxygen, then you need the oxygen delivered there. If you're running a marathon, then your muscles need the oxygen delivered there. Your body has to figure out where it needs it, and it uses the Q of the partial pressure in that particular area. Or also, then it also these graphs also suggest that there's other cues it uses as well. It relates to temperature, CO2, and pH, because these things can change the structure of hemoglobin and then change how tightly oxygen will bind to it. Yes, no. What's still confusing? People don't seem convinced. I see a lot of skeptical looking faces on my screen.
I guess I don't understand then, I get that part of it, but then I don't know, maybe it would be helpful to do that question
okay,
too.
Let's look at the problem. Okay, let's look at what this one says. This one is just comparing them. So it says at a partial pressure of oxygen of 20 millimeters of mercury, how much more oxygen is released in an exercising muscle cell whose pH is 7.2 than by a cell with a pH of 7.4. So think about this. If a pH is 7.2, what does that mean?
It's more acidic.
It's more acidic. Why is it more acidic?
There's more hydrogen ions.
Yeah, but when do cells usually become more acidic? When they're doing what?
Exercise.
Exercising. And why do they become more acidic? Because when you exercise, what do you produce?
Lactic acid.
Yeah, and you produce acids and you produce CO2, right? Just by the process of cellular metabolism. I wonder if that's part of the problem, is that we didn't talk very much about metabolism. Let me just a sec. Okay, I'm gonna pull up something from a class that you never took, and I haven't taught in a million years. So it'll take me a second to find it.